Picture a piece of iron the size of a tree trunk, glowing the color of a sunset, lowered onto an anvil the size of a house. Above it, suspended on rails 10 stories tall, hangs a block of solid iron, weighing as much as 6 elephants. A man pulls a lever, the block falls, and for one violent instant, the ground itself flinches. Nobody inside that building even looks up. It happens too many times an hour to register as anything unusual anymore. Somewhere nearby, a woman is hanging laundry on a line 2 streets from the forge wall. She doesn't look up either when the ground thumps under her feet. She stopped flinching years ago. Her husband is the one standing inside that building, close enough to the anvil to feel the heat coming off the metal before it even glows. Neither of them would call this normal, exactly. But it's their normal. It's the only normal this town has ever known. For nearly 200 years, machines like this one shaped the steel skeleton of the modern world. The axles under your trains, the crankshafts in your ships, the barrels of your cannons. They were called drop hammers, and they were every bit as dangerous as they sound. This is the story of the men who stood beside that falling iron, day after day, year after year. Some of them went deaf before they turned 30. Some of them breathed in dust that scarred their lungs for the rest of their lives. Some of them never came home at all. And in towns built around these forges, the ground shook so often that people stopped noticing, until their houses started cracking. It built the modern world. It is also, quite literally, still rotting men's lungs and ears, in forge buildings that, in some cases, are still running today. Before we're done, you'll understand exactly what that cost looked like, and why so many men paid it without ever being told the price. Here is the question we're chasing. How did a single falling weight become one of the most dangerous, most essential, and most quietly devastating machines in industrial history? And why are people still paying for it? We're not just talking about the men who stood next to it either. We're talking about entire towns. Entire neighborhoods built within earshot of a machine that never asked permission to shake their foundations. Keep that in mind as we go, because the damage in this story spreads a lot farther than the factory walls. To answer that, we have to go back to a problem that nearly stopped the entire industrial revolution in its tracks. By the late 1830s, engineers had a crisis on their hands. Ships were getting bigger, locomotives were getting heavier, and every one of them needed a single piece of metal that nobody on Earth could make: a paddle shaft, a crankshaft, an axle forged from one solid mass of iron, sometimes 30 inches thick. The old method was a sledgehammer crew, 10, 20 men, swinging by hand, in shifts, for hours, trying to beat a glowing slab of iron into shape before it cooled past working temperature. It was slow, it was inconsistent, and for anything truly massive, it simply did not work. The iron cooled faster than men could hammer it. That was the antagonist, a wall of physics that human muscle could not punch through. Think about what that actually looked like on a foundry floor before this machine existed. A glowing slab of iron, pulled from the furnace, had only a narrow window of time before it cooled too much to shape. During that window, a crew of men swung sledgehammers in rotation, as hard and as fast as they could, racing the clock against the iron's own temperature. Miss that window, and the entire piece went back into the furnace to be reheated, wasting fuel, wasting hours, wasting money. For a modest axle or a simple tool, that was merely inconvenient. For the kind of massive forgings the new steamships and railways needed, it was nearly impossible. No crew of men, no matter how strong or well coordinated, could deliver consistent, controlled force to a piece of metal that size before it cooled past working temperature. The bigger the project got, the more obvious it became that human muscle had reached its ceiling. A Scottish engineer named James Nasmyth ran into that wall directly in 1839. He needed to forge an enormous paddle shaft for a new steamship, and no hammer crew alive could do it. So he sketched something nobody had quite built before: a heavy iron block, lifted by a steam-powered piston, then released to fall under nothing but gravity and engineered weight, straight down onto the workpiece. The steam only had to lift the block. Gravity supplied the force no crew of men could ever have matched. He wasn't the only one who saw the same wall. Across the water in France, an engineer named François Bourdon had been sketching something almost identical, and when the two men eventually compared notes, it set off a bitter dispute over who deserved the credit. Both had arrived at the same brutal solution to the same impossible problem, independently, within months of each other. That alone tells you how badly the world needed this machine. What had taken 20 men an entire day now took one machine and a handful of operators an afternoon. This wasn't a modest improvement on the old method. It made the old method obsolete almost overnight. When the first of these steam hammers went into operation, witnesses described something almost frightening to watch. A tower of iron and steam, taller than a house, slamming down with a sound like a cannon firing, again and again, controlled by one man at a lever. Visiting dignitaries came specifically to watch it work. Foreign royalty toured working foundries just to see the thing strike. It was treated less like a tool and more like a spectacle, the kind of thing kings and dukes asked to see in person. People weren't entirely sure whether to be impressed or afraid. Mostly, they were both. But could it actually work, day after day, without tearing itself apart? That was the real test. Anyone could build something impressive for a single demonstration. Keeping it running, reliably, strike after strike, week after week, was an entirely different problem, and one nobody had solved before. The first real tests pushed the machine to its limits almost immediately. Engineers were forging shapes and sizes that had never been attempted before, and there was no guarantee the iron, or the machine, would survive contact. It did, and once it proved itself, demand exploded. Within a few short years, hammers like it were forging the axles, shafts, and gun barrels behind nearly every major engineering project of the industrial age. Foundries that adopted the new hammer early found themselves with a competitive advantage so large that hesitating meant going out of business. The machine wasn't an upgrade. It was a line in the sand. Adapt, or get left behind by someone who did. What nobody fully reckoned with, in all that excitement, was the question of what it would actually be like to stand next to one of these things for an entire working life. The engineers solved the metallurgy. They solved the steam pressure. Nobody in those early years was solving for the men. They'd built the beast. Now came the hard part, because making a tower of falling iron work reliably, every single day, without killing the men standing next to it, that was a completely different kind of war. 90 tons of falling iron. To understand why this machine was so dangerous, you have to understand what it actually was. Strip away the romance, and a drop hammer is a very simple, very brutal idea. Take a heavy mass, lift it high, and let it fall onto something soft and glowing. Gravity does the rest. The largest of these machines, built later in the 19th century, stood taller than a 3-story building and could weigh as much as 90 tons, more than a fully loaded jumbo jet. The falling weight alone, the part that actually struck the metal, could weigh dozens of tons by itself. When it dropped, it didn't just hit the iron. It hit the ground beneath the whole building, and the shock traveled outward through the earth like a localized earthquake, over and over, sometimes hundreds of times a day. Here is the chain of violence, link by link. Steam pressure forces a piston upward inside a cylinder, dragging the hammer block up with it on guide rails. At the top of the stroke, the operator releases the steam. Gravity takes over. The block falls, faster and faster, until it slams into the glowing workpiece, resting on the anvil below. The impact reshapes the metal in a fraction of a second, and sends a shockwave through the floor, the walls, and every bone in every body standing nearby. How did they actually control something that violent with any precision at all? Largely through feel and experience, rather than any fine-tuned mechanism. An operator learned, over years, exactly how much steam pressure produced. There was no digital readout, no automated feedback loop telling him he'd misjudged it. There was only the sound of the strike, the look of the glowing metal, and his own accumulated judgment standing between a properly shaped axle and a ruined, wasted piece of steel. But here's what made it genuinely terrifying to operate. The same force that could forge a battleship's crankshaft could just as easily forge a man's hand into the anvil if his timing was off by half a second. There was no clutch. There was no gentle setting. Once that block was released, there was no calling it back. The engineers who built bigger and bigger versions of this machine were fighting a problem most people never think about. Where does 90 tons of falling force actually go once it hits the ground? Early hammers shook their own foundations apart. Buildings cracked. Nearby walls developed fractures that spread, year after year, blow after blow. Engineers had to design entire foundation systems, massive timber and masonry platforms sunk deep into the earth, just to keep the machine from destroying the building it lived in. Get the foundation wrong, and the hammer would eventually shake itself loose, misalign, or tear itself apart from the inside. So the machine wasn't just a hammer. It was a controlled, repeated, engineered earthquake, contained, barely, inside a brick building, with men standing close enough to feel the heat of the iron and the violence of the strike on every single blow. How big did these things actually get? Big enough that standing next to one made a grown man feel like a child standing next to a barn. The largest examples weighed roughly as much as a small fleet of city buses stacked together, and when the falling block dropped, the impact could be felt through the floor of buildings well outside the foundry itself. Engineers measured the shock the same way seismologists measure tremors, because functionally, that's exactly what it was. A man-made, on-demand, repeating earthquake, scheduled for every working shift. That scale created a problem nobody had faced before. Nothing this massive, falling this fast, had ever needed to be controlled with this much precision. The materials available at the time were being pushed right up against their limits. Cast iron guide rails had to hold a falling weight perfectly straight, strike after strike, without warping or cracking under repeated shock loading. A kind of fatigue stress that engineers of the era were still learning how to predict. Get the metallurgy wrong, and the hammer itself could fail catastrophically, sending iron fragments flying in every direction. It's worth pausing on just how much trust that demanded of everyone standing nearby. A man feeding metal into that machine wasn't just trusting the operator's timing. He was trusting that the iron rails above his head, forged by hand using methods still being refined in real time, wouldn't be the thing that failed that day instead of the steel he was shaping. That kind of trust, repeated thousands of times across a working life, asked something of these men that rarely gets acknowledged in the history books that celebrate the machine's output. And then there was money. Building one of these machines, and the reinforced foundation required to keep it from shaking itself apart, represented an enormous capital investment for any foundry, often more than the value of the building it sat inside. Foundries that couldn't afford the investment found themselves unable to compete with the speed and precision of those that could, which meant the pressure to build bigger, faster hammers never really let up. Other countries and competing engineering houses raced to build their own versions, refining the design, scaling it upward, each trying to outbuild the last. Not every attempt succeeded. Some early competing designs proved unstable under repeated heavy use and had to be abandoned or rebuilt entirely. A quiet reminder that this was still very much an unfinished science, even as the machines kept getting bigger. And that violence didn't stay inside the building. The sound and the shock traveled. We'll come back to exactly how far, because the answer is more unsettling than most people expect. The gearing, the guide rails, the steam valves, all of it was brilliant engineering. But it had one vulnerability nobody fully respected until the bodies started piling up. It was a machine built around the idea that men would stand right next to it, hour after hour, for their entire working lives. Nobody had asked what that would do to them. The men who lived inside the thunder. If you've never stood near a forging hammer at full operation, here is what it actually sounds like. Not a thud, but a crack, sharp and immediate, like a gunshot fired at point-blank range, repeated every few seconds, for an entire 8 or 10 or 12-hour shift. Imagine a young man on his first week at the anvil. Call him no one in particular, because he was, in truth, thousands of different men across thousands of different forges, each with a different name and the same first week. He's barely out of his teens. His father worked this same floor before him, and his grandfather before that. He's been told the noise takes getting used to. Nobody told him that getting used to it actually meant his own hearing slowly leaving him, one shift at a time, in a way he wouldn't be able to measure until the damage was already permanent. Modern measurements at working drop forge plants have recorded peak noise levels from the hammer strike itself reaching as high as 154 decibels, louder than a jet engine at takeoff, measured at close range. Average noise exposure for the men actually running the hammers has been measured well above 100 decibels across a full shift. To put that in perspective, hearing damage can begin at levels above 85 decibels. These men were working at levels 15, 20, even 30 decibels above that, every single day, for years. So how did they survive it? Mostly, they didn't, not with their hearing intact. Studies of forge workers have found that more than 60% reported hearing loss, and audiometric testing at one hammer forge facility found that more than 80% of workers had measurable, significant hearing damage. The damage didn't arrive all at once. It crept in, blow by blow, year by year, until a man in his 30s found himself unable to hear his own children talking across a dinner table. But noise wasn't the only thing attacking these men's bodies. The machine reached them through their hands just as forcefully as it reached them through their ears. Hand-arm vibration is what happens when tools and machinery transmit constant, repeated shock directly into a worker's hands and wrists. Around drop hammers, this showed up in tongs operators used to hold red-hot metal steady through every single blow. Vibration traveling up through steel tongs, into fingers, into wrists, blow after blow, thousands of times a shift. Medical investigations into forge operations have documented workers developing nerve damage in their hands. Numbness, tingling, a slow loss of the fine control needed to do the very job that was destroying them. One documented case involved a hammer operator diagnosed with a debilitating wrist condition directly tied to the repetitive, forceful gripping required to hold tongs steady against the force of the machine. Think about the cruelty baked into that. The skill the job demanded, a steady hand, perfect timing, absolute control, was the exact thing the job slowly took away. And then there was the air itself. Forging shops were thick with smoke from coal and oil-fired furnaces, fine particulate thrown off by grinding and finishing work, and fumes from the lubricants and compounds used to keep dies from sticking to red-hot steel. Respiratory disease among forge and foundry workers has been documented for more than a century. Men who spent decades breathing shop air, developing chronic lung conditions that showed up only after they'd already given the best years of their working life to the hammer. Picture the air in one of these buildings, on an ordinary working day. Coal smoke from the furnace heating the next billet of steel. Fine gray dust hanging in the light from grinding the rough edges off the last batch of forgings. A haze of oily smoke rising off the dies every time hot metal pressed down onto them. None of it was ventilated the way we'd expect today. Men breathed all of it, all shift, every shift, for years. Lung disease tied to this kind of chronic exposure didn't announce itself with a dramatic symptom. It crept in as a persistent cough that never quite went away. Then a tightness in the chest. Then, decades later, a diagnosis that connected all of it back to a forge floor the man had left years earlier. But there was a quieter poison in that air too. One with no smell and no warning at all. Coal and oil-fired furnaces, burning in a poorly ventilated brick building, produce carbon monoxide, a gas so old to industrial workers that it earned its own grim nickname, white damp. It has no color, no smell, no taste. It doesn't announce itself with smoke the way an open flame does. It simply displaces the oxygen a man's blood is trying to carry, quietly, until headaches and dizziness and confusion set in, and a worker has no idea why he suddenly can't think straight, standing 2 feet from the furnace he's tended 100 times before. In a building already roaring with noise and glare and heat, a slow gas leak was the one danger a man's senses were the least equipped to catch. Our young apprentice at the anvil wouldn't have known the name for what was making him lightheaded on a poorly ventilated afternoon. He'd have just assumed it was the heat. Sometimes it wasn't. So how did the body cope with all of that at once? The noise hammering the ears, the vibration hammering the hands, the dust and the gas hammering the lungs and the brain. The honest answer is that it didn't, not fully. It endured, for a while, because the alternative was no wage at all. And then, sooner or later, something gave. Workers gave these machines names, and the names tell you everything. Men who spend their lives next to something that could kill them in half a second don't talk about it gently. They joke about it, darkly, because the alternative is thinking about it too much. Running one of these machines safely required an entire crew working in silent, practiced coordination, because shouting instructions over the noise was often pointless. Could a man even hear a warning shouted from 10 feet away over the crack of a falling hammer? Frequently, no. Crews developed hand signals, timing learned through repetition rather than verbal instruction, and an almost instinctive sense of when the next blow was coming, because relying on speech in that environment simply wasn't reliable. An operator's entire skill set boiled down to timing and judgment under conditions where a half-second of hesitation or a half-second of impatience could be the difference between a clean strike and a disaster. That kind of expertise took years to develop, and yet it was rarely treated or paid like the highly skilled trade it actually was. What was the worst job on the floor? Standing at the anvil, holding the tongs, feeding the hammer, closer to the blow than anyone else, trusting your reflexes and the operator's timing with every single strike. One mistimed release, one slip of hot, sweat-slicked tongs. That was the margin these men worked inside, shift after shift, for their entire careers. It wasn't only the men's bodies that paid for it either. A forge worker who went deaf in his 30s couldn't hear his children calling him from another room. A man whose hand had gone numb from years of vibration couldn't button his own coat without thinking about it. The job didn't just take hours out of these men's lives. It took pieces of the life waiting for them at home, quietly, in ways nobody at the time was tracking on any company ledger. For months, for years, they kept it running. The hammer never seemed to tire. The men did. And on the days it all went wrong fast. When the silence never came back. Every dangerous machine has a moment that defines it. And for drop hammers, that moment wasn't usually one single catastrophe. It was an accumulation, a staircase of smaller disasters that most people outside the forge never heard about. It starts small, a near miss. A man's sleeve catches on a guide rail at the worst possible second, and only a fast grab from a coworker saves his arm. It happens again, somewhere else, with someone else, and gets written off as bad luck rather than a warning. Then, it escalates. Records and medical case studies from forge operations describe injuries ranging from crushed fingers to severe hand trauma, the kind that ends in amputation. Injuries directly tied to the unforgiving, split-second timing the machines demanded. The mechanism was almost always the same story told 1,000 different ways. A worker's hand lingered on the workpiece a fraction of a second too long, or the operator released the hammer a fraction of a second too early, and there was no mechanical safeguard standing between that small human error and a catastrophic outcome. Unlike a cut or a burn, this kind of injury offered no warning and no chance to react. The gap between everything being fine and everything being permanently changed was measured in a heartbeat. Throughout the era of industrial forging, surgeons documented an entire category of trauma, built almost entirely around machines like this one. Crushing injuries to hands caught between dies, between hammer and anvil, in the half-second window where a worker's timing failed and the machines did not. In the 19th century, before modern anesthesia and antiseptic technique were standard, an industrial crush injury severe enough to require amputation carried a real risk of death from the surgery itself, not just the original accident. A man could survive the hammer and still lose his life to the infection that followed the operation meant to save him. Could they save him in those cases where the injury was severe enough? Sometimes. Often the best a surgeon could do was stop the bleeding and remove what could not be repaired, and hope the patient's body could withstand the shock of the procedure itself. A crushed hand wasn't just an injury. For a man whose entire livelihood depended on physical labor, it was frequently the end of his career and the beginning of a much harder, much poorer chapter of his life. And then there's the damage that doesn't show up as a single dramatic headline at all. The damage that simply accumulates, year after year, until a man in his 40s can no longer hear a conversation in a quiet room, or can no longer make a fist with his dominant hand. There was no single newspaper headline for that kind of injury. No dramatic accident report, just a slow, silent toll that took decades to fully reveal itself, and that, for many of these men, never appeared on any safety log at all. Go back to that young man we imagined at the anvil in his first week. Fast forward 20 years, and he's not young anymore. He's the senior man on the floor now, the one new hires watch to learn the timing. He still loves the work, in the strange, stubborn way men love things that have taken pieces of them. But he leans in close when his wife talks to him at dinner, because he can't quite catch every word the way he used to. His right hand goes numb sometimes in the cold, fingers refusing to fully close around a coffee cup. He doesn't think of any of this as an injury. He thinks of it as just what the job costs, the way every job costs something. Nobody at the forge ever sat him down and told him the bill would come due this way. It simply did, a little at a time, until one day he looked up and realized how much of himself the floor had quietly kept. That's the particular cruelty of this machine's danger. A boiler explosion makes headlines. A severed hand makes headlines. But a man losing 60% of his hearing over 20 years of standing next to a forging hammer? That happens so slowly, it barely registers as an accident at all, even though the hammer caused it just as surely as if it had struck him directly. And it wasn't only the men inside the building who paid. Drop hammers, by their very nature, send their violence outward. The shock waves they generate travel through the ground for considerable distances, and the noise carries for miles. Historical accounts describe steam hammers loud enough to be heard across entire towns, audible streets away from the foundry that housed them. People living near these forges didn't choose to be inside the blast radius of a machine they didn't operate, weren't paid by, and had no say in regulating. But they lived with the same percussive shock, the same relentless noise, day after day, simply because they happened to live near the works. In forge towns, this wasn't a rare inconvenience. It was the rhythm of daily life. Houses near the largest hammers reported cracking plaster and shifting foundations from the accumulated, repeated shock of decades of strikes, vibration powerful enough to be measured and engineered against, inside the very buildings that housed the hammers, let alone the structures next door that had no such protection at all. The same force that engineers fought to contain inside reinforced foundations was, quite literally, leaking out into the homes of people who had nothing to do with the forge at all. A family in a house 2 streets over from the forge didn't sign up for an industrial career. They didn't get a wage for what they put up with. But their windows rattled on the same schedule as the hammer's strikes. Their children grew up associating the cannon crack of falling iron with something as ordinary as a clock chiming. Sleep, conversation, the quiet of an ordinary evening. All of it was negotiated around a machine they had no say in, owned by people they likely never met, running on a schedule set entirely by someone else's production targets. Picture a mother trying to settle an infant to sleep in a house that close to the forge wall. She learns quickly that there's no fighting the schedule. The hammer doesn't pause for a crying baby, so she adapts instead. Feeding, rocking, soothing, all of it timed loosely around the rhythm of strikes she's long since stopped consciously hearing. Visitors to the house notice it immediately, flinching at every crack. She doesn't react at all anymore. Her nervous system has simply adjusted to a noise she never agreed to live next to in the first place. This is the part of the story that rarely gets told. The cost of these machines wasn't contained to a factory floor. It radiated outward, into entire communities, in the form of noise nobody could escape, and vibration nobody had agreed to live with. Pollution from coal and oil-fired furnaces drifted into nearby neighborhoods as a matter of routine, decade after decade, long before anyone seriously measured what it was doing to the people breathing it. Smoke that blackened the men's lungs inside the forge didn't stop at the factory wall either. It settled on washing lines, crept through windows, and coated the same neighborhoods that absorbed the shockwaves. What did the people living nearby actually do about it? In some cases, remarkably little, because the forge was also the reason the town existed in the first place. It paid the wages that built the houses being shaken. Complaining too loudly about the noise risked complaining about your own paycheck, or your neighbors, or your landlords. That tension, between needing the forge and suffering because of it, is its own quiet tragedy, one that rarely made it into any official record at all. It's worth sitting with that tension for a moment, because it explains why this kind of harm went on for as long as it did. A forge town wasn't just a collection of people who happened to live near a factory. It was an entire economy built around the assumption that the shaking, the noise, and the smoke were simply the cost of having work at all. Children grew up there. They went to school there, played in streets that rattled on schedule, and many of them eventually walked through the same forge doors their fathers had, because it was the only steady wage the town had ever offered. The danger wasn't hidden from them. It was simply normalized, generation after generation, until it stopped looking like danger at all and started looking like just the way things were. Regulatory response, when it eventually came, arrived agonizingly slowly. Occupational noise limits weren't seriously enforced in many forging operations until well into the latter half of the 20th century. Investigations conducted by health and safety agencies in more recent decades, at forge plants that had, in some cases been operating for more than 100 years, continued to find worker noise exposures exceeding safe limits, hand-arm vibration levels above recommended thresholds, and audiometric records showing measurable hearing loss across the workforce. In other words, this isn't purely a story about the distant past. Some of these exact hazards were being documented and confirmed at working forge plants within the last few decades, meaning, in some very real sense, men were still paying this price long after the world had the knowledge and the tools to stop it. And what about the surrounding neighborhoods, decades later? Environmental and noise regulation eventually caught up to industrial forging in most developed countries, restricting hours of operation, mandating sound barriers, and in some cases, pushing the loudest operations out of residential areas entirely. But that protection came generations after the first families had already lived their entire lives inside the blast radius of someone else's machine. The regulation arrived. The damage it was meant to prevent had, for many of those families, already been done. The dead and the deafened were never given a parade. The hammer kept running. The town kept shaking. But somewhere in there, the question everyone eventually had to ask out loud was this: was the steel really worth what it cost the men standing next to it? The buildings that still remember. So what did all of this actually buy us? Quite simply, the modern industrial world. Drop hammers and their steam-powered descendants forged the crankshafts of the ships that carried global trade, the axles beneath the railroads that connected continents, the gun barrels and armor plate that decided wars, and the heavy machine components that made the rest of the Industrial Revolution possible. Before these machines existed, there was a hard physical ceiling on how large and how strong a single forged piece of metal could be. After them, that ceiling simply disappeared. Entire categories of engineering, bigger ships, bigger engines, bigger bridges, became possible because somewhere, a falling weight the size of a small building was driving steel into shape with a force no group of men could ever match by hand. But the buildings that housed these machines tell their own story, separate from the steel they produced. Many of the original forge halls built around steam hammers are still standing, more than a century later, some preserved as monuments to the engineers who designed them, some converted into museums, and remarkably, some still operating today, the descendants of the original machines having been replaced gradually with hydraulic and mechanical presses that could deliver controlled force without quite as much raw, gravity-driven violence. What ultimately pushed the original steam hammer toward retirement wasn't safety reform, it was precision. Hydraulic and mechanical presses offered something a falling weight never could: consistent, measurable, repeatable force, blow after blow, without the wild variability of pure gravity. As manufacturing demanded tighter tolerances, the raw, brute force drop hammer gradually gave way to machines that could be controlled with far greater accuracy. Though notably, many of those replacement machines inherited the very same noise and vibration hazards that had plagued their predecessors, simply in a different mechanical form. The danger didn't disappear, it evolved. And that's really the uncomfortable truth sitting underneath this entire story. We tend to talk about industrial machines like this one in the past tense, as if the danger belongs entirely to old photographs and sepia-toned newsreels. But forge operators today, in plants that have been running continuously for over a century, are still being measured for noise exposures above safe limits. Workers today are still showing up on audiometric tests with measurable hearing loss tied directly to time spent standing next to a hammer. This damage is still happening right now, quietly, inside working buildings that most of us will never see the inside of. What does that mean for the towns built around these forges? Many of them still exist, still shaped by the industry that built them, even where the original steam hammers have long since been retired or replaced. The houses that once cracked under the shock of falling iron are still standing, in some cases owned by descendants of the same families who lived through the worst of it. The forge is quieter now in most places, but the relationship between a town and the machine that built it, that dependence, that quiet endurance, never fully went away. It just changed shape, the same way the hammer itself eventually did. That's the real legacy of the drop hammer, not just the ships and the railroads and the bridges, as real and as important as they were, but a permanent, ongoing reminder that some of the machines that built the modern world never stopped extracting their toll from the people who ran them, and from the people who simply happened to live close enough to hear it. The shaking faded from public memory. It never fully faded from the bodies of the men who stood closest to it, or from the foundations of the houses that absorbed it for decades, without ever being asked. We look at a drop hammer today, silent now, in most cases, parked behind glass in a museum or a preserved foundry, and we see a monument to engineering ambition. But it's worth remembering what that monument actually cost. Ears that never fully recovered, hands that lost their grip years before they should have, lungs that carried shop air for decades, and entire neighborhoods that lived inside the shockwave of someone else's progress without ever being asked. Stand in front of one of these preserved hammers today, and it's almost impossible to imagine the noise that once came out of it, the way the floor used to move, the way an entire street used to brace, without quite realizing it, every time that block of iron fell. The silence is the strangest part. These machines were built to be loud, built to be felt, built to announce themselves through brick walls and city blocks. Seeing one standing still, roped off, captioned with a small plaque, is almost a kind of disguise. It hides exactly how violent the ordinary working day around it used to be. Somewhere, in some town, there's likely still a man, older now, retired from a floor that doesn't exist in the same form anymore, who still leans in a little too close when someone speaks softly to him. He'll tell you the hammer gave him a trade, a paycheck, a sense of purpose that carried his family through decades most people only read about in history books. He'll also tell you, if you ask him plainly enough, exactly what it took from him in return. He won't say it bitterly. He'll just say it plainly, the way men who've made peace with a hard bargain tend to talk about it. That's the whole story, really, distilled down into one ordinary retired man and one ordinary retired machine, each of them having given everything they had to the work, and each of them a great deal quieter now than they used to be. They don't run the old ones much anymore, but in some forge buildings the thunder never really stopped. It just got a little quieter and a little easier to ignore. Progress had a price. A great many men, and the towns built up around them, paid it without ever quite being told the bill was coming.